Leetcode 230, kth smallest element in a BST. And of course, BST here means binary search tree. So it's a special case of tree, which is binary, meaning that there are at most 2 children at each level. And here we have some examples, and each circle can point to at most 2 other circles. Those are those children. And search term here means that there is an additional order imposed on a tree. And of course, we will use it. And this order is the following, that the left children is the data stored in the left child is always smaller than the data stored in the root, in the parent. And the data stored in the right child is always greater than the one stored in the parent. And that's it. Like, that's the whole philosophy. And we are given the root, so the first element, not the whole tree itself, but the first element. But because each element or each node stores connections to other elements, mainly to its children, we store connections only in one direction. That's why it's a tree and not a graph. And then we can use those connections, those left and right elements. You can check them here on the right side. That's the definition of a class, tree node, and we'll have an object of that class given here as our input. And using those connections left and right, we can traverse, go through each element, or maybe not each element, because we don't need to go through each, since we only want to have the kth smallest element. And of course, because it's a BST, we can do it in a very efficient manner, because there is this order imposed. And the other thing that we have is the integer k, and we want to have the kth smallest value, and we assume that we start from 1, not from 0. So the first, if the k is equal to 1, then we want to have the smallest. If the k is equal to 3, then we need to first find the smallest, then the second smallest, and the third smallest will be the one that we have to return of all the values of the nodes in the tree. And that's it. So the description is very scarce, nothing really here other than what we learned already from the title. And now let's take a look at examples. So we have following example. This is some strange representation, but we have a picture and we have k equal to 1. And of course, k equal to 1 means that we want to have the smallest element. And since there are only 4 elements here, we can already see that the smallest element is 1. And that's the output. And in the next example, we have 6 elements. And we want to have the third smallest. So 1 is the smallest. Then second smallest is 2. And 3 is the third smallest. And this is the option. This is the output that we have to return. Now let's copy that. And we have already said that binary search tree meaning at most 2 children. And guaranteed order. Order where left less than parent less than right. Like this. And now let's do maybe both examples. So that will be the first example. Why doesn't want to write like this? And 1, 4, 2. So how can we find the smallest element first and then the kth smallest element? Well, if the left is always less than the parent, then if we go to the left as much as possible, then at some point we will reach the smallest element. And of course, going as deep as possible means, or is called in a professional language, DFS. DFS traversal. And the next thing is that, of course, in a tree we can have, there are like 3 different types of DFSs. 1, 2, and 3. And 1 type of BFS. BFS is level order, like going horizontally 1 by 1. And DFS can be pre-order. Pre-order meaning that first we have the pre, meaning the parent, then left, then right. Then the one that is interesting to us right now, which is in order. Yeah. If you go in order, then first you get the smallest element, then second smallest, and so on. Yeah, but to have it in order, you have to go left, parent, right, and the last one is post order. When those two are swapped. Yeah, so first you go to the right and then to the parent. And here we want to have the in order version, or the in order strategy. That's the one that's interesting for us. So first DFS, then in order. And if we go as deep as possible, let's also give the second example. 5, 3, 6. Six and 2, 4, 1. This. So we keep track of the current element, and we go as deep as possible using in order, and then we backtrack and we try the right path once. Yeah, as deep as possible, so as many as possible to the left. Then if there are no more left, we go to the right, but just once. Yeah, and then again and again until we reach k elements, or until there are no elements left. So in the first example, we would go like this. So first we start always from the root, then we go to the left, like this, and that. And because k is equal to 1, that's already the end, and we don't do anything else. In this case, we would go like this, like this, and here, yeah? And that would be our smallest element. Then we try to go to the right. There's nothing there. We backtrack. Yeah, go one above. We try to go to the right. Nothing here. And then finally here. And that's our k was equal to 3. So that's already our answer. So we reached this point. Here we incremented k to be 1, and then 2, and then 3. And that's it. And we didn't explore those because we don't need to. And in this case, those two as well. So the whole algorithm is as follows. We start at the root. We keep track of the current. We go to the left as deep as possible. We try to go to the right once and repeat from here there, but between those two we also do one more thing. We increment the counter and check with k. And so we need to also have some counter of how many times we repeated this operation. Like this. And let's add some arrows to make it clearer. Maybe a little bit smaller. And now let me just draw that. Because we'll repeat it in a loop. And of course, we can either use iterative or recursive approach. Both are possible here. And in case here, one more thing, we can terminate if those are equal. Terminate like this. So we have some counter, we check how many times we did it, and that's it. If the counter is equal to the k, then we terminate if equal. That's the whole algorithm, and it works graphically the way we did it here. And so first we go as deep as possible, we try to go to the right, if not, we go up, and each time we increment some counter and check if it's already equal to the one that was given as the input. So let's first create a stack where we'll be pushing our current nodes, and we start from the root. And while there is something in either stack or current, we continue. And first we want to go as far as possible to the left. We add to the stack current first, not current, and then we move to the left. Yeah, and now we can pop from the stack the next element. And decrement the k. Yeah, so either we create an additional counter that we increment here and we want to reach k, or we decrement simply k by 1. And if k is 0, then we can return current value. Or sorry, val. I think it's val. Yeah, it's val. The next thing is, the last thing actually, is to go to the right. Yeah, so current equals current. Right. And let's try. And while current left. Okay, so here simply while current. Yeah, because at this point it can already be done. Let's submit. See how it goes. And we beat 100% when it comes to the runtime and 93% when it comes to the memory usage.